Thank you. Thanks for coming. Yesterday I talked about QCD. Now for the remaining 7 lectures, we're going to be talking about different aspects of time, and especially its symmetries. This will lead us in many directions to ideas about what the dark matter of the universe might be, to ideas about new useful materials in engineering, very interesting materials that we don't know what they're going to be used for, and in the final lecture, even into biology. Now, in this lecture, I'm going to give a broad introduction to the question of symmetries of time that will show that there's a unity, a unifying vision behind all these different applications and areas that we'll be talking about in more technical detail in the later lectures. So without further ado, let me bring in St. Augustine, one of the fathers. Wrote a book called The Confession, biography, maybe in the first modern autobiography. And in chapter 11 of that book, he discusses time. This was provoked by a question from one of his parishioners who asked, what was God doing before he created the universe? And St. answered, he was preparing people to ask questions like that. But the question stuck with him, and he kept thinking about it, and came to some very interesting conclusions in chapter 11 of that book, which is it's very funny in an autobiography. It's really a learned philosophical discussion of the nature of time, and we'll come back to St. Augustine. But to begin this discussion, here's a very famous quotation from chapter 11. What then is time? If no one asks me, I know what it is. But if I wish to explain it to him who asks, I do not know. I think we all know that feeling, that he felt that way about time. Well, now we can give an answer to that question. What is time? And here it comes. Time is the thing that appears in time derivatives in the equations of physics. In the equations of physics, there's something called t, which corresponds to our intuitive sense of time, but is much more precise. It tells us how things change. It tells us that all things change according to the same measure, which we abstract and therefore call time. And time has certain properties. Besides being a universal variable in which we express the laws that are valid everywhere, and it has a kind of tangibility because it has properties like symmetry and we can, from this abstract notion that there's this thing that controls change, it takes on a life of its own when we can say it has certain properties. And very powerful properties of time are its symmetries. Two symmetries in particular, which will be the focus of our attention. One is called capital T, and that's time reversal symmetry. It's the fact that the laws of physics, the fundamental laws, look very much the same if you imagine changing the sign of t in all the equations and also changing other things in appropriate ways, like magnetic fields have to change their direction. We'll discuss this in considerable detail next time. And that raises all kinds of questions. We'll even find that it might give us the essential clues to what the dark matter of the universe is. That's a story we'll be building up. The other great symmetry of time doesn't have a name that is commonly agreed to in physics or a label. So I've invented one. I call it tau. Tau is time translation symmetry. That means you can take the laws of physics, take this t that appears in the laws of physics, add a constant to it, and you get the same laws again. It's another way of, so that's a property that t is, that can be, it's uniform. So it's like, if you think of it as a line, it's uniform. The line has no distinguishing marks on it, and also it can be flipped over. That's time translation symmetry. So those are what the symmetries of time tell us. And tau is effectively the fact that the laws of physics are forever. They don't change. So now let's hone in on these concepts, define them more precisely, and see what questions they raise. Starting with T, time translation symmetry. And to me, this is, in the present state of physics, is the road to axion. That's the frontier of our understanding of time reversal symmetry. And it's a very exciting frontier, as I hope to persuade you. So the laws of and change of time since acceleration, the basic equation is this time doesn't change the acceleration. And it just as you reverse the sign of time. And this can be extended, as I will discuss at a technical level next, the laws of electron, laws of almost all standard models, really valid symmetry of physics. In fact, the first violation of time reversal violation in the fundamental law was discovered only in 1964 and came as a big surprise to people. It came about in sort of an obscure corner of physics having to do with the decays of very unstable particles, decay mesons. So the laws of physics are very nearly symmetric under this transformation, but the physical world is not. Look around. People are getting older, not younger. Light is shining from the light bulb, not going back. Ways in which the are seem there's all radiative tends to go out in our experience, not in from decaying bodies or bodies that are heated up. There's the thermodynamic arrow of time, the famous second law of thermodynamics, which says that the entropy of an isolated system increases in time. So that's definitely not the same as the reverse direction. There's the psychological arrow of time. We remember the past, but only guess and plan about the future. And many others you could address. So this situation raises two profound questions. One, why do the laws have this symmetry? The job of physics is to describe the world. The world doesn't seem to have the symmetry. Why do the laws have it? It seems like a gratuitous feature that we didn't need. And in fact, it's an embarrassment because we have to explain the difference between the fundamental laws that have this symmetry and the world which doesn't, in many ways, as we've seen. So, present-day physics, present-day science, has impressive but partial answers for both of these questions. We've made progress, but we haven't solved them completely. For question 2, that is, how can the world, why does the world look so different going to the past versus the future with all these different arrows of time? I think there's a convincing story that shows that these many different arrows of time all can be derived from one. That is, if you say that the early universe began in something like the Big Bang. The Big Bang was an expansion of the universe, but you could imagine eventually it would collapse again. So how does that violate time reversal symmetry? Well, it's not just that there was a bang at the beginning, but it was a very unusual, very strange beginning. That is, in the Big Bang, the matter was very, very uniformly distributed and very hot. This is a picture, famous microwave background radiation, which is kind of a snapshot of the universe 100,000 years after the Big Bang, which was that was the infancy of the universe. And if you looked at the night sky at that point, people were around, which of course they weren't, but if they were, they would have just seen a uniform haze. It's only if you turn up the contrast by 10 to the 4th and look in the microwave region, because the photons at that time have been expanded and redshifted as the universe expanded, you see a picture like this. So it started out very, very uniform, much more uniform than we see today with galaxies and lots of empty space, and very, very hot. So what does that mean in terms of what was likely to happen? What was this condition? Well, the fact that it was hot at a very high temperature means that matter was in equilibrium with its interactions. Okay. So we assume that the strong electromagnetic and weak interactions, all the fundamental interactions, were in what's called thermal equilibrium, in their most likely sort of random condition. And that gives a very good model that has many consequences in cosmology. But we add to that the assumption that it was approximately uniform based on these observations. That means that although matter was in equilibrium, gravity was not in equilibrium. Gravity was as far from equilibrium as you could imagine. Gravity wants things to clump up. So if gravity is left to do its work for a long time, things will clump up, make stars and things like that. But at the beginning, it was very uniform. So we had equilibrium with respect to matter, gross disequilibrium with respect to gravity. And ever since, the history of the universe has been gravity trying to get into equilibrium. So the universe expands, but gravity clumps things together, makes stars, galaxies. When stars get very dense, they start to liberate nuclear energy. You make planets. Planets irradiated by that energy can support complex structures, life. All the other arrows that we discussed can be derived just from the idea that early in the universe we had matter in equilibrium, but gravity way out of equilibrium. Here's a picture that shows the evolution of the universe. So that's question 2, where we have a picture that's not universally accepted, but it's right. And there's many details to be worked out, but I think that shows that all the arrows derive from just one arrow. That is the fact that the Big Bang occurred with this very special character, equilibrium for matter, this equilibrium for the non-gravitational interactions, this equilibrium for the gravitational interactions. And the whole history of the universe since has been gravity trying to restore its equilibrium. What about question 1? Why do the laws have this T symmetry in the first place? Well, there's a convincing story. Well, I'll try to convince you of it in the second and third lectures here in this series. There's a convincing story that almost derives that strange fact from other deeper sacred principles, namely the fact that we want the theory of relativity to be enforced, the principles of quantum theory, and the deep symmetry, the gauge symmetry of the Standard Model, which tells us what kind of matter actually exists in the world, and it's constrained by powerful symmetry principles. The possible interactions are constrained by relativity, quantum mechanics, and the structure, in particular the gauge symmetry of the Standard Model. We'll discuss this in great depth in coming lectures. And based on that, the possible forms of interactions are constrained by those sacred principles, and you find that if you impose those constraints on the possible interactions, the possibilities for T violation, almost by accident, are very, very limited. Okay? So the other principles, these deeper principles, give you the T invariance to a very good approximation as a consequence, a kind of accidental byproduct. The basic ideas of this explanation were given by these two people, these two Japanese physicists, Kobayashi and Masukawa, who won the Nobel Prize for it, because they predicted, they showed that the interactions are very, very constrained by the sacred principles, and you can almost not get time reversal. You can almost derive time reversal symmetry. But remember, I also told you that in 1964, experimenters found that time reversal symmetry is not quite exact. Their analysis showed that there's just one kind of interaction that's allowed by the sacred principles, but violates time reversal symmetry. It's a very special interaction in part of the so-called weak interactions. And when it was proposed, that was a very bold kind of speculative idea. But since then, it's been proved by discoveries in particle physics and further investigation. And now it's won the official seal of approval of the Swedish Academy. But it's wrong, or at least incomplete, because their analysis overlooked a possibility that emerges from deeper scrutiny of the Standard Model. There's another possible interaction that also could violate time reversal symmetry. It's a funny interaction between the color gluons that I discussed yesterday of a very particular kind. So there's another possible interaction which they didn't think about. But nature also doesn't use it. So that's a puzzle. So we thought we had understood why time reversal symmetry is as good as it is, but actually it's a little bit better than our current explanation. If you put a numerical measure to this coincidence, this fact that there's an interaction that could have happened as far as the sacred principles are concerned, as we understand them, it should have occurred sort of using dimensional analysis ideas with a strength of 1, but the measured strength is less than 10 to the minus 10th. So that's something we don't understand in a spectacular fashion, even within 10 orders of magnitude. Is that a coincidence? Well, let's hope not. Such a strikingly small number should have a qualitative explanation. And over the last 40 plus years, since this problem took shape, there have been several attempts to explain why that occurs, why this interaction, which is allowed by sacred principles, but violates time reversal symmetry in a way that's not seen in nature, why it doesn't occur. But only one has stood the test of time. Little joke there, test of time. It's that a theory of evolution for that coupling constant, the strength of that interaction. Instead of it being a number that's fixed forever, according to this theory, it's known as Peche-Quinn theory after the physicist who first introduced it, that number should actually not be considered as a number, but should be considered as something that is a dynamical quantity that can change in space and in time. So we expand the standard model to have a new degree of freedom that makes something that used to be a number into something that can vary. And if you do it in the right way, everything's got to be quantum fields in fundamental theory that respects quantum mechanics and relativity and the basic structure of the standard model. If you do it in a way that's simple and natural, you find that it's possible to introduce a complex field into the standard model, an additional complex standard field with a scalar field with 2 degrees of freedom. It's a complex variable. It has a magnitude and a phase. And the phase corresponds to that extra parameter. And as the universe evolves, I can't show a picture with every point having a value of this field, but just this is a typical point, and you have its magnitude and its phase. It settles down as the universe evolves to a place that corresponds to that parameter that's very small, in fact, being very small. But a consequence of this picture, this theory of evolution that tells you this very, very small parameter got to be that way by being something that can change and actually changing, has a remarkable consequence. It predicts the existence of a new kind of particle called the axion, named after a laundry detergent by me, because it cleans up a problem in fundamental physics. And I just thought this sounds like a good name for a particle. Sorry. And as a big bonus, which we'll be discussing in the next couple of lectures, we'll discuss this whole line of reasoning in depth, but I'm just showing you where we're going. As a big bonus, you find that this axion particle has just the right properties. It's produced in the right amount in the early universe. It is produced nearly at rest. This is so-called cold dark matter. And it interacts very, very weakly with ordinary matter. It has just the right properties to provide the mysterious dark matter that cosmologists need. What is this dark matter? I'll just very briefly remind you or tell you what it is. One finds, or astronomers have found, in many, many different circumstances, that there's more gravity than can be ascribed to the matter we see. So, using standard astronomical techniques, you can see light from stars, you can see radio waves from hot gas, you can see many, many different signatures of the kinds of matter we study in the standard model, the kinds of matter we're built out of, the kinds of matter we understand very well. Even neutrinos, you can sense neutrinos from the distant sources nowadays. But if you add up the gravitational influence of all those things, you find that it's not enough to account for the motion of things in gravitational fields in the universe. Or an additional manifestation of gravity shown in this dramatic picture, the lensing of light by gravitational fields. So what you're looking at here is, to get used to this, there's a black hole. All right, can we get rid of that? All right. What you're looking at here is an image of the distant part of the universe that's been distorted by the gravity of a cluster of galaxies that comes between things that are behind and us. And the gravitational influence of that cluster of galaxies bends the light. Bends the light of things behind, so you can get to see many copies of one galaxy. It's like you're looking through the end of a glass soda bottle. You see many copies of this distorted image. And these galaxies out here, which look suspiciously the same, they're actually the same galaxy, just multiply imaged, because the massive object inside has bent the light, and now it has more than one way of getting to us from behind. And if you ask how much bending can be due to the influence of the galaxy or the cluster of galaxies in the middle that is doing the bending, there's just not enough matter there. You need about 6 times more matter than is visible, than the astronomers can account for. So that's what's called the dark matter. It shows up in many ways, and we don't know what it is yet, but many of us suspect that it's these axions. And so that wasn't put into the theory, but is a very encouraging thing if you think that sort of automatically, without trying for it, you solve a problem that is a very big problem. People have put a lot of effort into trying to find these axions. Here you can see many, many different experiments and observations that are meant to address the problem. Here is where the theory tells you you should lie in the parameter space of mass of the axion versus the strength of its coupling to photons if it's going to be the particle that solves the theoretical problem that axions were designed to solve. And experiments are just beginning to get into this region, and I'll discuss how that's happening and what the prospects are for progress. And here, this blue intersection, that's the sweet spot where the axions quantitatively supply exactly the amount of dark matter that's needed in astronomy. And as you'll see, there are experiments which are getting very close to testing whether there actually is a particle in this region. See, most of the existing experiments have either been in the wrong place or not sensitive enough, but we're getting better at doing these things. And it's in the target zone. Here's what the detector looks like schematically. The basic theory tells you that axions in the presence of a magnetic field can turn into photons, and photons are things we know how to detect. These are actually microwave photons. So a lot is known about how to detect and deal with microwave photons. That's called microwave engineering, and summarized in this eyeball. And in the presence of a magnetic field, axions can turn into photons, and then we try to detect the photons. Now, really, the experiment has a bit more sophistication than that cartoon. In order to encourage the axions, which interact very, very weakly, to turn into photons, you fill the cavity with specially designed materials or antenna-like instruments. But now it's not antennas to define radio waves or the kinds of things that are broadcast by radio and microwave stations, but the axion background requires a different kind of instrument. And this is an example where you fill the cavity with an array of wires that you can tune to look for axions of different frequency or mass. You need a big magnet, and here's a whopping big magnet that is going to be put into service of the search. And you need very sensitive instruments to detect the microwaves because there are not very much of them. The axions interact very, very weakly, so we have to make sure that we can detect even a small number of photons that they generate. And as I mentioned, we're getting there. So this experiment, which I'll describe in some detail in the third and fourth lectures, will get us into the sweet spot where axions are predicted to find the dark matter. And we'll see whether that's true or not. This experiment is being built at the Wright Laboratory, and I'll show you pictures of the collaboration and things like that as we go on. Now let me discuss, this should be material, not meterical, or whatever that is. There's a typo here, so ignore the C. And we can also have time reversal violation in materials. So far I've been talking about fundamental time reversal, that symmetry. That is, if you are looking at interactions in empty space, but you can also look at physics inside materials to see whether that respects this principle that you can reverse the direction of time and get the same equations, or equations with the same consequences. And this has been a very fruitful thing to think about. So, time reversal violation in matter can have many consequences, and or we consequences are also sometimes called signatures, if you want to know whether a material, in fact, has managed to spontaneously organize itself in ways that violate the principle of time reversal symmetry. So one is if you have correlations between magnetic and electric moments. So if you have electric dipole moments, so polarization, so your material has things that are nicely aligned with positive and negative charges. And then you also have magnetic moments, so you have spins that are aligned. If there's a consistent correlation between the directions of those moments, that violates time reversal symmetry. Because if you think about it, a magnetic moment is associated with a spin or a current that's going around in a circle. If you reverse the direction of rotation, which is what happens if you change the direction of time, then the magnetic moment changes sign, but the electric moment does not. So this dot product, if you apply time reversal, changes sign. If it's not zero inside a material, then that material breaks time reversal symmetry. In general, this gives you possibilities of changing magnetism into electricity. And if you apply a magnetic field, the material will respond with an electric moment. Or if you apply an electric field, material will respond by producing a magnetic field. So that gives us ways that you'll see are very, very powerful to control, if we have such materials, or if biology has such materials, control the interactions between electric degrees of freedom on the one hand, and spin or magnetic degrees of freedom on the other. And then there are a bunch of other effects which we'll go into as these lectures develop. In general, a very, very powerful strategy in engineering and in biology and in technology is to be able to change one kind of thing into another. So, for instance, if you can change mechanical effects into electrical effects, you can do things like have amplifiers on guitars, because they respond to the vibrations of the sounding board and turn them into electrical signals, which you can use to drive amplifiers. So having mechanisms of changing one form of energy, one kind of response into another, this kind of transduction, is extremely powerful. Just to give another example, this is piezoelectricity, when you change stress into electrical signals, or in general, piezoelectric materials allow you to change electrical things into mechanical things and vice versa. And that can be used, for instance, to make clocks. You apply an electric signal, you have something that vibrates. When you have something that vibrates, you can count how fast it vibrates, and that's the principle of quartz watches and things like that. So this is very powerful. Another example that's very germane to this time reversal issue is if you have time reversal violation, as I discussed, you have the possibility of changing electric moments into magnetic moments and vice versa, or in other words, of using electricity to control magnetism and magnetism to control electricity in versatile ways. That sort of thing is very much used in computers because electric degrees of freedom are subject to stronger forces than magnetic degrees of freedom. So if we want to manipulate information, for instance, we move charges around. But if we want to store information in a more stable form, we use something that's less weakly interacting, We use spins. We have magnetic memories. We want to change one into the other. It's a very useful thing to do, to be able to manipulate energy, store it, and then come back and have it ready for us for use later on. Okay, so thinking about fundamental properties of time reversal is allowing us to design materials with these desirable properties, so-called metamaterials. And we'll be discussing that. And we'll be discussing biological T violation. This is a subject in the making, I think. But it's a continuation of a grand story that goes back to the 19th century. Not time reversal symmetry, but spatial inversion. So instead of changing the direction of time, you change x into minus x instead of t into minus t. So spatial inversion or parity transformations are known to change the structure of biology. It's known that biology does not respect the principle that physics does to a very good approximation of allowing you to change x into minus x and get the same laws. Like time reversal symmetry, this for a long time was thought to be a fundamental property of the laws of physics. It was only in 1956, with the theoretical work of T.D. Lee and C.N. Young, and then the experimental work of Madame Wu, that parity violation in fundamental law was discovered. But biologically, it's an older story. In biology, going back to Pasteur, you find that there are manifestations of parity violation, in particular something called optical activity, which we'll come to in a moment, that is characteristic of biology and distinguishes between left and right-handed behaviors. Nowadays, when we understand biology at a more molecular level, we know that in many cases, we have molecules that have both left and right-handed forms that are distinct, that can't be superposed on one another. And in those cases, the two different kinds of molecules, which are physically, in their physical properties, basically identical because they're related by parity, which is basically a symmetry of fundamental law, have very, very different biological activities. So what Pasteur discovered was that when he distilled a particular substance called tartaric acid from ferments that were made biologically, and you formed crystals out of that material, that the material only formed one kind of the two possible crystals, distinguished by being reflected in the mirror. Whereas if you look at samples of the same material that were produced by more physical means that didn't involve living objects, you would always produce equal amounts of the left and right-handed crystal. And if you take the same substance and dissolve it in a fluid, you find the property of optical activity, which is also a signature of distinguishing left and right. That is, if you take plane polarized light and put it through a sample, the plane of polarization rotates by an amount proportional to the length of sample you put it through. And if you think about it, I invite you to try to visualize this. That violates the parity, the equality of left and right, the fact that it rotates one way and not the other. It's like a screw, you're rotating one way and not the other. And this is now widely used as a signature of the biological origin of substances, and is understood at a molecular level because if you have amino acids, they're built out of building blocks that are carbons, hydrogens, amine groups, NH2, carboxyls, and different kinds of additional materials. And if you think about arranging these four things, you can arrange them in two ways that are not superposable on one another, but related by mirror reflection. One is right-handed and one is left-handed. And it's because of this that biology displays an asymmetry, because only one out of this group is typically made in biological substances. That's why you have an asymmetry between left and right-handed. And it's passed from generation to generation in the form of templates that govern early development. How could it be that generation after generation you have, despite the fact that physical law is equivalent between the right and left hands, the biology isn't? It can only be because it's inherited from, you have a template that goes on from one generation to the next. We don't know how initially this asymmetry between right and left hands crept into biology. Some people have proposed that it comes in through the effect of the tiny asymmetry of physical law and the weak interactions that somehow gets amplified. But I think much more reasonable and under active investigation is the hypothesis that parity violation occurred because of local conditions like a magnetic substrate. Magnetic fields violate time reversal symmetry, where life originated. This suggests experiments, as I'll discuss, and we can see if this hypothesis really leads to successful predictions. So, to summarize this part, we have questions. I'm trying to raise questions in your mind that we'll be addressing. So, how did the parity asymmetry of life emerge? This probably happened very early in the history of life and may give clues as to how life itself originated. And then, can patterns within the choices be deduced from physics and chemistry? What I mean by this is that if you have some physical effect that's distinguishing left and right, it makes certain reaction patterns in the biological world more favorable than other reaction patterns. Can those patterns be seen in the actual choices? So we have choices of many different molecules that are left and right. So in principle, those could be all independent, but physics might suggest that they're not all independent, that if you choose one kind of asymmetric molecule, then the other one has to be a particular choice that fits it. Now, moving from this inspiring story of parity to time reversal, biology manifestly violates time reversal in big ways. Babies develop. Adults don't undevelop back into babies. People get older, not younger. Evolution started with very simple forms of life, single cell creatures. Eukaryotes were messed up with sloppy DNA into much more sophisticated objects, and in any case, different objects as time goes on. People learn, so individuals also change with time by gathering knowledge and so forth. So many, many ways in which time reversal is violated in the phenomenon of life and biology. But as I argued before, I think we can trace all of these ultimately to the fact that there are gradients of energy and entropy that are present inside cells and inside organisms that tend towards equilibrium. But the disequilibrium that's necessary in order for that to occur comes from the radiation of the sun, which comes out and towards us and definitely violates time reversal and all the other uses of energy to drive reactions in one direction and not the other, ultimately derive from that radiance of the sun. And the sun itself, as we've seen, derives its radiance back from the Big Bang, from the fact that it condensed out of uniform matter and got very dense so that nuclei could burn again. So ultimately, you're getting older because the Big Bang was in the past. Now, much less obvious and a frontier of research is if any non-dissipative time reversal symmetry occurs in biology at the molecular level, similarly to how parity violation occurs in biology at the molecular level. That would, so why would that be a useful thing? Why would evolution want to do it? Well, one way is if you want to sense the direction of magnetic fields, you need to have a kind of meter, a kind of substance, kind of a thing that responds to one direction differently from the other, that you can read out. Okay? If you were put in a dark room and had a compass that wasn't labeled north and south, you wouldn't know how to label it. You need something that tells you how to do it. And this is a very pressing question for certain kinds of bacteria, because these bacteria are very impoverished, or we might say stupid, in their sensing of the world. They're very, very small. They're down beneath the ocean. They don't have brains. And they face a challenge, which is they want to be in a certain region of the ocean where the oxygen level is right for them. In fact, they want to be in a place where there's very little oxygen. These are ancient creatures that originated when the Earth had very little oxygen, before the onset of modern plants, which injected lots of oxygen into the atmosphere. So they want to find this place, and in the dark, in the ocean. How do they do it? Well, one strategy is to follow the Earth's magnetic field. Then they won't wander around aimlessly, but they'd be able to follow the magnetic field lines. And how do they do that? Well, they make themselves into magnets. There are these marvelous bacteria, so-called magnetotactic bacteria, that construct within themselves tiny nanomagnets, strings of them, and put them together, and that allows them to passively, just like a compass needle, follow the Earth's magnetic field, and so they can move efficiently to where they want to be. And this is a labeled compass because it's constructed in a way that's systematic and starts from one place where you have an origin and it accumulates. These guys attract, they take magnetite out of the ocean and manufacture these very beautiful little nano crystals, very perfect, very flawed. They're small enough so that they're single domain technically, and there's a string of them, and that's how they manufacture time reversal violation and use it in navigation. Now, as I mentioned, that could be useful not only for that ability to transfer information between the world of electricity and the world of magnetism, could facilitate, in general, transfer of information between charged world and spin world, and the possibility of moving information from places where it's easily processed into places where it's easily remembered. This is something that's used in computers. Is it used in biology? Well, we're trying to find out. It's very encouraging that these ancient creatures already had a way of making these worlds communicate, and we suspect that that ability was passed on through the tree of life. So, questions. Did these remarkable capabilities of magnetotactic bacteria percolate up the tree of life? And is this seemingly powerful, potentially very powerful method of transferring energy between charged world and spin world actually a significant theme in deep biology? So is it something that evolution not only should use, but does use? We'll find out. So much for time reversal. And as I said, we'll go into much greater depth in all these things in the coming lectures. Now I'd like to turn to tau, time translation symmetry, the other fundamental symmetry of time. We'll see many of similar questions arise, similar features, similar basic contrasts. And the most basic of them is very reminiscent of what we saw for time reversal symmetry. That is that the laws of physics are very nearly symmetric under time translation. In fact, we think they are exactly symmetric under time translation, but the physical world is not. Okay? I talked about the many ways in which you can distinguish past from future, but that also means that things are developing systematically as things get older. Time is not uniform. There is such a thing as history. Now, first of all, what is the evidence that the laws are invariant under time translation symmetry? This is maybe the most basic principle of science, that the laws don't change as time goes on. So you can do experiments tomorrow based on what you did yesterday and expect them to work in the same way. Well, the most far-reaching test of this idea is based on looking at the light or other electromagnetic radiation from distant objects. And you can study in great detail the pattern of spectral lines that emerges from distant objects. And of course, that pattern of spectral lines is a consequence of the laws of physics acting on stellar environments and atmospheres and things like that. And you can see, do the same laws work a long time ago in the same way as they work today? And once you take into account the fact that there's an overall redshift because the galaxies are moving away from us, so a kind of Doppler shift, the pattern of spectral lines maps accurately between very different epochs in the age of the universe. So it does appear, and you can test this in great detail by looking at the details of these spectra, it does appear that the laws are operating in the same way today as they did billions of years ago with very impressive accuracy. Another thing you can do to test time translation symmetry, or the basic symmetries of time, is compared clocks of different composition. Nowadays, clocks, atomic clocks, and clocks based on basic principles of physics can be designed, and these clocks are accurate to a part in 10 to the 20th or so. That is, if you had two of these clocks and they ran for the lifetime of the universe, they would get out of sync by no more than 1 second. Now, you can't actually run them for the lifetime of the universe, but you can run them for 1 day and measure small fractions of a second and see if they get out of sync. And since you can make different kinds of clocks based on different materials, different applications of the laws of physics, if those laws were changing as a function of time, the clocks would go out of sync. So you don't have to look at distant galaxies. You can just look very carefully at things in nearby laboratories, and again, get very accurate tests of time translation symmetry, and it works. Another profound test of time translation symmetry was due to this, is due in essence to this woman. This is eminent, who proved within the context of general principles of Hamiltonian mechanics, so mechanics, she didn't realize it, but it was this is necessary in the formulation of quantum theory. She proved a theorem that relates the existence of conservation laws to symmetry. I think Xingdong gave you an introductory lecture about this connection between symmetry and conservation laws due to eminent. So with different kinds of symmetry, there are always associated conservation laws according to this theorem. So for instance, the symmetry of physical law with respect to translations in space is connected, can be deduced from, and vice versa, is equivalent, according to Noether, to the invariance of the laws of physics with respect to translations in space. The conservation of angular momentum is associated with the invariance of physical law with respect to rotations. That laws look the same in different directions. And then finally, the conservation of energy is associated with translations in time. Now, you've been taking physics courses recently and have been exposed to different forms of energy. I remember when I was a student, I thought this was a gigantic cheat. Okay, you start with a concept of energy, which is, okay, things move, and so there's a measure of how much oomph they have, so that's kinetic energy. But that's not conserved. So you introduce another kind of energy, you introduce potential energy, and okay, and that's for conservative force fields, that's fine. You get now you've restored the conservation of energy. Then you come to electricity and magnetism, and you find, oh, energy is not conserved again. We have to invent another kind of energy, field energy. We put in the field energy. And you come to more advanced parts of physics. There are other new laws and other kinds of energy. Why does this keep happening? And is there any content to this, or are you just going to keep fixing it when it doesn't work? Well, because of this connection between symmetry of time time translation symmetry and conservation of energy, we see that there's a reason why conservation of energy keeps coming back. It's because it reflects the symmetry of physical laws, the fact that they don't change as time goes on, that they have a kind of eternity to them. So, just as for T, just as for time translation symmetry, these properties of tau symmetry raise two basic questions. Why do the laws have tau symmetry? Why are they invariant, given that the world isn't? Why do we need that property? And then secondly, given that we have that property, why does the world violate it? The laws don't, but the world does in many ways. Or maybe it doesn't. I'll come to that at the very end. So these philosophers, David Hume and Immanuel Kant, this is Hume, that's Kant, had deep discussions of this question of why the laws of physics or the laws of science are invariant under time translation symmetry. Hume said, it's just a fact, and you can't derive it from anything else. And in fact, it might fail tomorrow. The sun, you have no reason to think that the sun is going to rise tomorrow, because tomorrow has never occurred before. You've never seen that circumstance. So how do you know? How can you infer logically what's going to happen? Kant proposed the theory, the idea that the world would be incomprehensible without this fact that the laws don't change with time. So in order to think about it at all, you impose on the world, or it's unthinkable that it would not be a time translation symmetry. I think neither of these approaches is the best we can do. What we can do is show that time translation symmetry is part of a bigger picture involving conservation of energy, involving testable consequences. We can see, we can really test that it's true. It's not a vague thing, and it's certainly not something that is imposed by observers on the structure of the world. The world does its thing, and we observe it. And certainly, the early universe could have looked very different logically. It's just an empirical fact, and we would still have been able to look at it and see that it was different, that the spectral lines didn't quite match. And in some respects, the world does change as a function of time. The distribution of matter, and we believe even in the very early universe, the masses of particles could change because Higgs fields could melt and all the particles become massless and things like that. And there's nothing incomprehensible about it. I've just told you what happens. So, we haven't really answered the question of why the laws of physics are time translation symmetric, but we can say that they are part of a very compelling story that can be tested in many ways. So similarly to the way we can align all the different hours of time and reduce them to one, we can reduce the discussion of why laws stay valid, why science is possible, to this principle of conservation of time translation symmetry, which we can test in many ways and that has many fruitful consequences. But the Big Bang happened in the past, not in the future. That sets not only a direction, but also an origin for time. And so both symmetries are broken by cosmology. Okay, I think I'm over time, so I'm going to just flash by. Time, maybe we'll come back to this. Time translate. the violation, the spontaneous violation of time translation symmetry in materials. I think I'd better come back to this next time. I will just resume at this point next time, but let me skip ahead to some philosophical questions about time translation symmetry, because I think this is very poetic and a good way to end this discussion today. So back in the 6th century BC, two Greek philosophers, Parmenides and Heraclitus, began a discussion of whether things change or things don't change. It seems like a very peculiar thing for people to be discussing, but the ancient Greeks were peculiar people, and they worried about things like this. So Parmenides was an advocate of the idea that nothing ever changes. So everything has always existed, nothing can come from nothing, nothing really changes. The appearance that things change is superficial, and we should insist on logic, and logic doesn't change, and so that means that the world can't really change. It's got to be eternal. Heraclitus was a representative of a more down-to-earth, empirical school of thought, empiricism. He says that everything changes. Obviously, look around, and the senses are reliable. So who's right? Maybe they're both right. If you think about the description of water flowing in a river, there are two very different descriptions that you might give, and in fact, that are widely used. One is usually associated with the name of Euler, the Eulerian description. In that description, what you do is at every place in the river, at every place in the fluid, you have a velocity. So you have velocities as a function of position, a field of velocities. And looking on the outside, that's sort of a God's eye view of what's happening in the river. That's a very satisfactory picture. But a different picture is from the inside. This is associated with the name of Lagrange. In mechanics, we have the Euler-Lagrange equation, so these guys appear together, but actually here they're at war with each other. So the Lagrange picture is you follow the motion of a fluid element. So you're looking on the inside. So instead of saying that the velocity at this place is something, you say that if I'm at that place, I move according to that velocity. And you follow the trajectory of the water molecules. But that's the picture you would get if you were actually part of the flow. And if you have a steady flow so that the distribution of velocities stays the same, that's what Parmenides would like. Nothing is happening in the river. It's unchanging in time. Nothing to see here. But at the same time, if you take the other point of view, from the inside, the Lagrangian point of view, you wind up with agreeing with Heraclitus that things, in fact, are changing. You move, or you find yourself in very different positions. Nearby parts of the stream might cross and crisscross, form vortices. All kinds of things can happen from the interior description, even when the God's eye point of view is not changing. And this same thing can happen in quantum theory. In quantum theory, we have not fluids, but we have wave functions that fill all space. And we can either speak of their velocity flows or the flows of probability in these wave functions. That's the interior description, or we can look at the wave functions themselves as functions of position. That's like the Euler description. And so there's two different ways of looking at it. And this, I think, is likely to be a very illuminating point of view for the interpretation of quantum theory. The interpretation of quantum theory, if you just look at the wave functions externally in the formalism, is famously problematic. Where's the observer? What is this observer you're talking about? Is it something not in the wave function? But if you go into the wave function, following the Lagrange point of view, then you can see a dynamical world emerging that can correspond to our impression of how the world works, that things really change. Well, I'm in the middle of trying to show that you can get universal computation, you can make Turing machines, and therefore minds within this framework, and that is a very interesting possibility. So, let me conclude. Going back to St. Augustine, so what is time? If no one asks me, I know what it is, but if I wish to explain it, I do not know. I hope you've seen that we can now say quite a few things about time. We can pose very pointed questions and make progress on them. And in the future lectures, we'll be exploring in technical detail these ideas, where they lead. And the one-page summary or the one-sentence summary of where we'll end up is, we're still working on it. Okay, thank you.
Now the lecture is open to questions. If somebody asks the question, please stand up and introduce yourself first. Yeah.
Well, so the question is, can the appearance of T violation in laboratory experiments at short distances, what we think of as the fundamental laws working at short distances, can that be superseded, transcended in a bigger picture where time reversal symmetry, you said, is maintained? So could there be a second universe where the opposite kind of time reversal is the opposite behavior of the laws, the opposite asymmetry is present, and the combination of the two would be symmetric? This is maybe easier to think about in the context of spatial inversion. So could there be a mirror universe in which everything that was right-handed turned into something left-handed and vice versa? So it's the kind of universe you see if you look in a mirror. Could there be a second universe? And if that universe existed, would it mean that overall parity was conserved, because you could have a kind of parity transformation where you change left into right and also change one universe into the other. So you have a bigger symmetry that's still maintained even though locally the symmetries are broken. And yes, that's certainly a logical possibility. But what's for sure is that locally we see violations of the symmetry. And that other mirror universe, if it exists, or its analog for time reversal, is not very accessible. So if we believe that the fundamental laws are local, that we can figure them out by looking at short distances, then we have an unequivocal answer that the symmetries are broken. But there is that logical possibility that you have mirror universes that at a more global level restore the symmetry. So it's a logical possibility, but I'm not sure it helps us very much to postulate other worlds that we can't access. Yeah. Yeah, hello. Yeah, sure. Good to see you again. Well, congratulations, and congratulations to TDLI for having you. Mm. Yeah. Yeah. Okay. So let me rephrase the question. And so the question was, what is time when we measure very, very short times? And does it change, or does it even lose its meaning if the time scale is short enough? So let me answer that in two ways, or three ways maybe. First of all, let me ask, because it's a little easier to think about, ask the same thing about space. Okay, so in space, our basic concepts actually that we still use today go back to Euclid. Euclid postulated that space is uniform, that it can be divided finer and finer. He, of course, back in the day, was thinking of rulers, and you divide the ruler finer and finer, and it still remains a ruler, and the properties don't change. Nowadays, we know that that's not true, that rulers are made out of atoms, and the laws on short distances are very, very different. You measure distances in very different ways that are very indirect. And so, yet, amazingly, the concepts of having a continuum and that space has translation symmetry, strict translation symmetry, not a lattice or anything, but strict continuous translation symmetry, that it can be divided infinitely fine. Those are still the basis on which we erect the laws of physics. I don't understand. I mean, it's amazing that those assumptions based on thinking about rulers, right, and measurements of farms, of distances, of surveying, which is where geometry came from, that those turn out to still be valid at ultimately short distances, even though the meaning of the words is completely different. And the way you actually measure distances is very sophisticated. You have to do a lot of analysis, and so you take X-ray diffraction patterns and piece them together and things like, and go deep inelastic scattering and see how things behave at very short distance. It's similar for time, very similar for time, in fact, but even more severe because our concepts of time are newer and sort of less familiar in everyday life than concepts of space, I would say. But we use exactly the same concepts for time that we use for space, that it's continuous, that it can be infinitely divided, that it has these symmetries, even though to measure very short times involves very different techniques. And you don't have clocks that you watch ticking, right? You do experiments with scattering things and very sophisticated analysis to see what's going on at short times. But the laws seem to work with at the theoretical level. The theories that work are based on these basically Euclidean concepts. And one other remark about that is that, of course, in relativity theory, which we think is pretty basic and has many successes, space and time get linked together. So the fact that you use the same language and basic concepts to describe both is not an accident. That's part of the structure of the world according to relativity. Okay, so now to your actual question, which is, are there reasons to think that this eventually breaks down? That if you go to short enough distances, short enough times, that we, and yes, there are reasons to think that things change at super duper short scales of time and space that we haven't yet even come close to accessing experimentally. These are the so-called Planck scale of length and time. The Planck length is 10 to the minus 33 centimeters, if I remember correct, or so, which is about 14 orders of magnitude smaller than anything we've measured even with very sophisticated techniques. And it's a similar story for time. The Planck time is like 10 to the minus 44th seconds, and the shortest time we can measure is much bigger than that. Many, many orders of magnitude bigger than that. What is the meaning of these Planck scales? Well, when you come to general relativity, space and time have dynamics. They can bend and change and distort. And then if you build in quantum mechanics, things that are dynamical also fluctuate. You have fluctuating. I talked about uncertainty relations, for instance. So that means things are uncertain and fluctuate. When you get to the Planck scale, the fluctuations in distance are as big as the distances themselves. So what distance means in that context becomes very unclear. And similarly in time, the fluctuations in time, the quantum fluctuations in time between two points that are that close together are as big as the separation itself. So it's not clear that those distances have operational meaning, or whether the mathematics that we inherited from Euclid will still work in that domain. So we don't know. I don't know the answer to that question. Nobody knows the answer to that question. The good news or the bad news is that it's very, very far removed from experiments we can actually do. Yeah. Well, okay, so this question is a kind of general question. Now that we're getting better control of the quantum world, we can do what's called simulation. So you can simulate different situations that before we could only dream of and write on paper what their specifications are. Now we can sort of build physical models of them. So we can build models of different materials and test their properties without having to run to chemistry labs, things like that. And people are getting better and better at that with the help of better control of the quantum world. And so it will be possible to test different ideas about how space and time behave at short distances, just as it's going to be possible to simulate how different speculations in particle physics or in the design of materials will work out. So yes, it will be. I mean, so the short answer is yes, it will be possible to do kinds of exploration by these kinds of numerical experiments that we can't do in ordinary physical experiments. And with the advent of quantum computers, we'll be able to do experiments in quantum physics very directly that we can't, that at present we can only sort of dream about. So that's certainly possible. But yeah. Yes. Yes.
I myself feel feeling very perplexed about this question. Is that how you measure or do have
Yeah.
going from the case of quality chemistry, where we can simply compare the angle between
Yes.
over the translucent view from the clarification that I mean we have direct way of having
Yes. Well, this is precisely the question that will be addressed in the next lecture in great detail. Exactly how you test time reversal symmetry and what its consequences are and how it is embedded in fundamental law. So next time we'll begin the more technical discussion of all these issues, and that will be the very first one. Okay. So.
Other question.
Yeah. Hello. Most what? Most the spectrum? Best prospects? Well, again, I have to refer you to a future lecture. I'm prejudiced, but I think I showed you the alpha experiment, which I am heavily involved in. I think that has alpha. It's called alpha, and I think that has excellent prospects. So I don't want to say that other experiments are worse, but alpha is very good, and we're hoping that we'll get to the goal. Yeah. Okay. Yes. Oh, yes. No. Okay, well, physics and science in general is ultimately an empirical uh, domain of investigation. So at any time, we might find experiments or observations that force us to change our understanding in basic ways. So this has happened historically on a few occasions. Maybe the most dramatic was the development of quantum theory, which really changed the picture of the world in very, very basic ways from classical physics. Even though classical physics was very successful in its own way. So it's not impossible that we'll have to unlearn things that we think we know very well, that the theory of relativity, quantum theory, or the structure of the basic symmetry structure of the standard model. It's possible, but there are mountains of success. There are mountains of evidence for the fruitfulness and power of those principles. People have been trying for years to find flaws and exceptions to these laws. You know, you get Nobel Prizes for things like that if you can find breakdowns of the fundamental laws. And now, for several decades, there's been no change in the fundamentals. And well, quantum mechanics is about 100 years old. Modern quantum mechanics, relativity is a little older than that. The standard model is even getting old. It's about 50 years old. So they've held up very, very well. So if any of them fails, that would be a profound discovery in itself, and we'd have a lot to explain how it could have been so successful, even though it's wrong in some way. Now, when we come to time reversal, if time reversal had been an exact symmetry of nature, we could have stopped there. That would be, I agree with you, that would have been a great principle. Okay, it's wonderful. It's very lovely. You can pronounce it in one sentence. It has a very, very clear meaning, intuitive meaning. And that would have been a very good stopping point. That could have been a fundamental principle. But it's wrong. So if it were true, it would be fine. But it's wrong. So you have something to explain. And so it's very important that we can't say that that's just the way it is, because it's not that way. And so what we can do, and what has been done with almost complete success, as I said, not quite, is to understand why time reversal is almost, but not quite, a property of the fundamental laws. So if it had been precise, we could have stopped there and been happy, and your question would have a lot of force. Why are you trying to explain this in terms of something else? But the fact that it's not true means that we can't do that. Yeah. Yeah. Yes, I claim that all macroscopic violations of time reversal symmetry ultimately can be traced to the Big Bang, and how matter was in equilibrium, but gravity was way out of equilibrium. And then you follow how a universe that starts that way develops, and you find our universe, including its time reversal properties. So there are many details that have to be worked out in substantiating that claim, but I don't think there's any I don't think there's any barrier to doing that, and a lot of it has been done, and the rest probably could be done. Yeah.
Maybe the last question.
Is time reversal symmetry based on time translation symmetry? No, they are distinct things. You can imagine lines that are homogeneous but don't have a preferred direction, or you could imagine lines that are not homogeneous but do have a preferred direction. So they are really independent properties. Okay, so maybe what you're asking, if I can try to interpret it, is if you try to make something that's imagine you have time reversal symmetry but not time translation symmetry, then you ask, why do you change t into minus t instead of changing t plus a into minus t plus a? Yeah, so if you're going to have time reversal symmetry without time translation symmetry, you have to have it around a certain point, or you could have it around several points. But they're independent principles, but if you have both of them, time translation symmetry is more powerful because then you can reflect around any point. Okay, but in principle, you could imagine that you can reflect around only certain points of time. If time is not homogeneous, if it's not translation invariant, you can still have points around which you can reflect. So, yeah, that's. What's that? Very what? Oh yes, it would be important in this circumstance, right? If it definitely, yeah. Well, that was the hypothesis. If time translation symmetry is violated, and yet you have time reversal invariance, then there have to be special points around which you reflect. And so you can't reflect around any point. You have to reflect only around certain points. This is something that arises for spatial translation symmetry and parity inside crystals, for instance. So you can reflect around certain crystal planes, but not others. And so you do have parity invariance, but you don't have translation in space. You can certainly imagine a similar thing for time. And in fact, I hadn't thought about this, but it's something that arises in time crystals. If you have time crystals, this exact situation could easily arise. Yeah.
Okay. I think we should freeze over. Come to the next lecture tomorrow. So let's
All right. Thank you. Okay. Okay, thank you.